So I would like to introduce the LAMpAS project, which is based on a new concept for providing technical surfaces with advanced functions. And in the title, you can see we are talking about how can we enhance such characteristic inspired by nature, and therefore let me show you an example. So we have learned from, the last years that if we are capable to control the topography of surfaces, which means to have very well-defined surface structure with feature sizes from the nanometer to the micrometer range, and of course also in combination with the appropriate surface chemistry, we can provide technical surfaces with very interesting properties. And I can believe you have here already, we can get, for example, an antibacterial surface or a surface with self-cleaning characteristics, or we can make optical security functions or the decorative effect, among others. But what is very interesting also to know, and is the example of this insect in the screen, is that by combining different length scales, we can even further increase the performance of these functions, or even to get multifunctional surfaces. And this insect, again, that you see in the screen, had kind of antibacterial properties. It's surviving in all weather characteristics, and the reason for that is that we can find on the skin of this insect, firstly, micro size structures that provide mechanical stability to this surface. And then this topography is decorated by very small features with a size of about 600 to 800 nanometers. And this is what brings at the end the antibacterial performance. So the big surface protects these small features which are bringing this antibacterial performance. And what we want to do is trying to bring these concepts to mass production, and of course using photonics technologies, using laser processing. And the only way to increase throughput or reducing fabrication times is first to have high power systems. We're talking on the development of 1 kilowatt, 1.5 kilowatt picosecond laser sources. And then we have to distribute this energy very efficiently in order to avoid, for example, heat accumulation problems. That brings to the high power laser processing paradigm. We have two possible solutions how to put this energy appropriately to the surface of our material. And the first solution is that we use relatively large spots where we provide the laser power on the material surface, and then we have to move these quite large spots with high scanning speed, for example, over 100 meters per second. But we have the problem again of the insufficient resolution, because we need to increase the spot size in order to process the materials correctly. The second strategy is, okay, we use smaller spot sizes. What typically you can get is 20 to 50 micrometers. This will require scanning speeds over 1 kilometer per second, which is possible today with some systems. But at the end, we even require to do lower, to get higher resolution in order to finally get these surface functions. Therefore, we come to the scenario number 3, and the idea is to use the concept of direct laser interference patterning, where we are putting two beams, for example, together, created a periodic variation of the laser intensity distribution. In this way, we can make smaller feature sizes on the spot size, and this helps us to reduce heat accumulation and simultaneously increasing the resolution. What kind of materials can be processed using direct laser interference patterning? In particular, every kind of material that is absorbing the laser radiation. And we have experience from the past with polymer systems, with coating, for example, diamond-like coatings, which are very interesting for reducing friction and wear. We can process steels, aluminum, several metals, as well as transparent materials. Regarding the feature sizes that have been possible to achieve so far, they are between 150 to 20 to 30 micrometers. Again, just by changing the angle between the interference beams, we are able to perfectly decide on the feature sizes that we are producing. Depending on the laser source, in particular, if we use nanosecond pulses, which is not the target of LAMpAS, we already have demonstrated to reach throughputs close to 1 square meter per minute, which is very interesting. And we are dealing with typical functions, regarding friction reduction, antibacterial, improvement of biocompatibility and decoration, and so on. So we have already processed quite large areas of close to 1 square meter per minute in some cases. Also, we are working on the structuring of replicating tools, for example, cylinders or sleeves that you can later use in roll-to-roll processes. And we have the chance to control very well the feature sizes, the geometry. Therefore, we can also create very interesting decorative elements, for example, or anti-counterfeiting elements. In particular, the image that you are observing on the bottom on the right side, this is a process stainless steel, it's not a draw, so we can perfectly design different optical colors that can be controlled again by having the correct surface pattern with the correct feature sizes. An example of application related large area processing, but we're using the replicating tool. So we have these structured cylinders and sleeves, and we have pattern polymer foils that can be reproduced at the speeds of 15, 20 square meters per minute. On top of that, we can deposit different cells, in this case, flexible perovskite solar cells, and we have reached an improvement of 5% in the performance. So to bring us now more to the objective of LAMpAS. So then the idea to get a high resolution and being able at the end to create all these kind of properties requires again the use of 2 or more laser beams to create the interference patterning. This is what we are going to, or we are actually combining with a high-speed beam deflection system, which is based on a polygon scanner. And this new optical concept will be implemented with an ultra-short pulse laser system, a high-power system from TRAMF with up to 1.5 kilowatt of laser power. And simultaneously, we are working also with 2 inline monitoring systems to control the structuring process, assuring that we can get different standards regarding to the functions of the surfaces we are treating. And of course, we had at the end the construction and integration of these submodules into a laser system. I would like you to define then shortly our objective. So again, for one side, the development of the high-power picosecond laser source, the development of the high-speed beam delivery system based on interference pattern and polygon scanners, simultaneously to develop 2 inline monitoring process to assess the functional performances, and the construction of the large system with all the different sub-elements. Of course, we're processing demonstrators with the high performance requirements, and at the end we will have a prototype that will be tested in a relevant environment. So far we have reached different results. From one side, we already have been able to construct a high power picosecond laser source. This is done by our partner TRUMF, and so far we reach 1 kilowatt of laser power. The laser source is based on disk technology, so we have the laser beam that is going through several times over the active media, and in this way we have very strong amplification of the laser power. Other results is regarding the inline monitoring systems. So here we are implementing 2 different system. From one side, we're using a camera system that we can detect heat accumulation. This has been so far evaluated with low power laser sources, as we can see maybe on the right side image. So this is the evolution of the intensity that are collected by the camera system, and depending on the process parameter, we have a different number of counts that can be correlated with the quality of the surface. I will show you later. And then also we are working with a so-called fast Fourier transform submodule, which allows us to detect characteristics of periodic surfaces that are produced, periodic structures that are produced on the surface of materials. So just to give you one example regarding the camera system, we have already identified, depending on the counts that are recorded by the camera system. So we have detected a limit where we start to observe heat accumulation problems, with the consequence that we have a significant deterioration of the surface quality. This has been also combined, as I mentioned before, with a fast Fourier transform monitoring system that also already allows us to detect specific features, what is captured by the camera system, and this also at least can help us to detect if the structure we are producing have a good quality or a bad quality. The combination of these setups is very strong, and we are now working in the next part of the project, how to record these signals with high speed, and also developing strategies to control the process. Other important result is also the development of a heat accumulation model. This is mainly done by LAMpAS and Bosch. That means we have already two algorithms actually that allows us to understand very well how we need to distribute the laser energy in order to avoid heat accumulation, which means how to bring the best surface properties and the best surface quality on our materials. Finally, I would like to show you the drawing of the final system that is being constructed right now by LAMpAS, where we are going to integrate our 1.5 kilowatt laser source, which will have a weight between 300 to 500 kilograms and very large size. This system is positioned below the machine on a drawer to reduce footprint and easy maintenance. And then we have also the integration of the high-speed beam delivery system, which will have a weight of about 45 kilograms and a relative long working distance that will bring also high flexibility for processing different parts that are going to be provided by our end users, which are Bosch and BSH in Spain. Okay, with this, I would like to thank you, and also, of course, Francesca and all organizers, and maybe we have some minutes for questions. Thank you.
Yes, thanks a lot, Andres. Thank you for giving us this nice introduction to the project, and also a bit the last status update. So in my opinion, it's maybe interesting for the audience to take the message now from the last slide, so how the situation is with the machine, and thinking a bit also towards the business development. So where do you think a part of our early adopter, that is, as you just mentioned, Bosch, who are the potential sectors, customers that we have in mind? So where is the strength of the application of LAMpAS, Andres?
Okay, firstly, we will focus on the needs, let's say, of our end users, Bosch and BSH, which are related to food industry processing, for example, and also on devices that are used by BSH. where we need a high throughput because we need to process a large amount of products per unit of time, and because the characteristics, the properties that you can get with this technology is very wide. The number of application cases that can be really huge. What we need is, time is money, and time is throughput. So if we increase throughput, we reduce time, and we reduce time, we reduce the process costs, and then the opportunities will be huge.